students, good morning, good evening and good night, depending on which time you are going to observe this lecture. Welcome to this 9th lecture on solution chapter. In this lecture we are going to discuss two different things. Number one, we are going to discuss the depression of the freezing point of the solutions, and number two, we will going to discuss the osmotic pressure. So heading of today's lecture is there are two different things that we are going to discuss in this lecture, that is depression of the freezing point of the solution and the osmotic pressure. In the previous lecture, 2-3 lectures, we have discussed in detail that when we add some involatile, non-volatile substance to a volatile substance in the solution, there is a drop of pressure of the solution that we have discussed in detail in the previous 2-3 lectures. And this drop of pressure in the solution is going to influence also the freezing point of the solutions, and it is observed that this freezing point of the solutions has been decreased as compared to the pure solvent. As we have discussed that there is a elevation of the boiling point when there is a incorporation of the non-volatile substance. Now in this lecture we will be able to discuss how there is a depression of the freezing point when we add this non-volatile solvent. And it is basically, we will understand after the discussion, that there is the main factor that the vapor pressure of the solution has been decreased. So this is K.K. Mukherjee, the Science with Mukherjee Sir YouTube channel. First we are going to discuss the depression of the freezing point. Let us understand, at the freezing point there is a dynamic equilibrium between the solid phase and the liquid phase. So we can able to define the temperature of the freezing point as that point in which the vapor pressure of the substance at the liquid phase and the solid phase is equal. That is the main thing that we will discuss. That freezing point is basically that point when the vapor pressure of the solid phase and vapor pressure of the liquid phase will be same, will be equal. So when solution going to freeze, going to be solidified by way of phase transformation, and that will only occur when the vapor pressure of the solution will be equal to the vapor pressure of the solid state of the pure solvent. So when this will be equal, at the time there will be the freezing of the solution into the solid state. So this can be also understand from this figure also. Temperature in the y-axis, there is a vapor pressure, and here you can see this is the graph relating to the pure solvent. This is the graph for the pure solvent. So you can write it is pure solvent. Pure solvent graph is this. That is the relation between the vapor pressure of the pure solvent and the temperature. And when this pure solvent has been freezed, at that time the solid will have some curve, and this curve is this. So this is the, you can write frozen pure solvent, you can write frozen pure solvent. Frozen solvents, frozen solvent. So you can easily understand at that point when it meets the pure vapor pressure, this is the vapor pressure of this pure solvent and the vapor pressure of frozen solvent. At that time, when the temperature, at that time the temperature is suppose TF0. Temperature suppose is TF0. TF0. And TF0 we can say that is the freezing point of this pure solvent, because at that time the vapor pressure of the pure solvent and the vapor pressure of the frozen solvent will be equal. Now when we add some non-volatile substance to this pure solvent, then its vapor pressure will be going to be reduced. At that time you can see its curve will be like this. This is the curve of the solution when we add the non-volatile substance to the pure solvent. And we know that vapor pressure is decreases. So from this curve, when the vapor pressure of the solution will be equal to the vapor pressure of the frozen solvent, then this solution will freeze, and that is not possible at that temperature TF0, that is the freezing point of the pure solvent. It will be the vapor pressure of the solution will be equal to the frozen solvent at the lower temperature. So we can write, you can extend this curve here. Here you can see it meets here. It meets there and it will be fine, you can see TF. TF, suppose the temperature of the solution at which it frozen, at which it become solidified. At that point, the vapor pressure of the solution and vapor pressure of the frozen pure solvent will be equal. So we understand that solution now freezes at the lower temperature as compared to the pure solvent. So this is called the depression of the freezing point. Depression of the freezing point, suppose it is delta EF, and it is equal to the TF0 minus TF. So this is called the depression of the freezing point. Depression of freezing point. Depression of freezing point. And it is also a colligative property because it depends on the number of particles, not on the nature of the particles, like the elevation of the boiling point of relative lowering of the vapor pressure. And in the dilute solution, you will find this delta F, that is the depression of the freezing point. You can write delta F is directly proportional to the molar concentration of the solutes in the solutions, means molarity of the solution. So it is directly proportional to this, and then we can write this delta TF, depression of the freezing point. There is a constant is coming, Kf into F. Kf is called, it is called the freezing point depression constant. It is also called freezing point depression constant. Freezing point depression constant. Depression constant. Or is also called the molar depression constant. It is also called molar depression constant. And another name is there, it is giving, that is a cryoscopic constant. Cryoscopic constant. So this Kf is characteristics of the solvent. This Kf, you can see Kf for water, it is 1.86. Kf for carbon tetrachloride, it is 31.8. Kf is basically the characteristics of the solvent, and the units of the Kf that we can easily understand. Kf, that is delta Tf by m, is molarity. Now this, the unit of the temperature is Kelvin, and the molarity is kg per mole. So mole per kilo, molarity is mole per kilo, so it will be kilo kg mole to the power inverse. So the units of, this is the unit of Kf is this, and it is characteristics of the solvent. So we can now, from this depression of the freezing point, we can able to calculate the molar mass of the solute. How do we calculate? Let us understand. Suppose there is, we have taken W2 gram of solute. We have taken W2 gram of solute in W1 gram of solvent. Suppose we have taken this. Then we can easily able to calculate the molarity of this solution. The molarity, suppose it is having, the solute is having, the molar mass is M2. At that time, molarity will be M is equal to, we can write W2 divided by M2 divided by M1 by 1000. So you can write this equation. Molarity is basically, you can see W2 into 1000. We take in the numerator. Now W1 into M2. So this is the molarity, and we just put this value here. So what we get? Delta Tf is equal to, we get W2 by W1 into 1000 divided by M2. Now M2 you will get, what you will get? Simple, you just interchange this. So W2 by W1 into 1000 divided by Tf. So you can get easily the molar mass of the solute by getting the depression of the freezing point. You can calculate, you can experiment this, and you will get this depression of the freezing point. So we understand the depression of the freezing point, how this depression of the freezing point occurred due to the lower vapor pressure of the solution, and what is Kf, that is constant, and also we understand how do we able to calculate the molar mass. Now we are going to discuss another thing, that is the osmotic pressure. To discuss the osmotic pressure. Osmotic pressure. This is also a very important colligative property, and this colligative property, from this colligative property we are also able to measure the molar mass of the solute. So what is osmotic pressure? For that we have to first understand the osmosis. To understand the osmosis, let us have take the reference of some phenomena that we have observed in our day-to-day life, in the nature or in our home. Like when we put the raw mango in a brine water, it shivers, means it deforms, that means producing the orchards and other things that we will find, that the deformation of the mangoes. And in this case also we observe, and another incident we will see, when we put some wheat flour in the water, it revives. And another thing that we observe, that is the bird cell, when it is put in a salt water, it collapses. All this phenomena that we observe in nature and in our home, that is basically, there is a common thing that we will observe, that it is this, most of the substance has been covered by a membrane, and this membranes, it appears to be a continuous sheet or a film, but there is a very minute submicroscopic network of pores or holes, and these submembranes, which has composed of these very submicroscopic holes or pores, this will allow the flow of the solvent molecules, which is smaller in size. The solvent molecule usually pass through this, but it will restrict the larger solute molecules. It will restrict the larger solute molecules, but it will pass the solvent molecules. And this type of membrane is called the semi-permeable membrane. This characteristics of this semi-permeable membrane. So you can write this semi-permeable membrane. Permeable. And this semi-permeable membrane, that is, has been written as SPM. And this semi-permeable membrane, when we put like this, suppose here figure, where in the left hand side you will find, in the right hand side you will find the solvent, in the left hand side is a solution. So this is the semi-permeable membrane. So what will going to happen due to its characteristics, that it will the solvent molecules, that is the smaller size of the solvent molecules, will pass through this semi-permeable membrane to the solution. And this type of flowing of this solvent molecule to the solution molecule is called the osmosis. So we can write this definition of the osmosis. Definition of the osmosis is, it is the flow of, we can write flow of solvent molecule, flow of solvent molecule to the solution molecule, flow of solvent molecule to the solution site is called the osmosis. Now we can see here there is a atmospheric pressure on the both the side. Now if we put some extra pressure, that is, suppose this is pi, this amount of extra pressure we put on this solution side, at that time what will going to happen? The solvent molecule will not pass. It will restrict, or the flow of solvent molecule will be stopped at this pressure, that is pi pressure. This pressure is called the osmotic pressure. This pressure is called the osmotic pressure. This pressure is called osmotic pressure. So we understand the osmotic pressure and osmosis. Osmotic pressure, it is the extra pressure that we put on the solution side, which will restrict the flow of the solvent from the solution side. So it is basically a pressure on the, it is an extra pressure, because already there is a pressure, atmospheric pressure on the solution and the solvent. But when we put some extra pressure on the solution side, we can write it is an extra pressure. It is an extra pressure which restrict the flow, which restrict the flow of solvent molecule to the solution. So this is called the osmotic pressure. And if we put some dilute solution and this concentrated solution, and this is separated by SPM, semi-permeable membrane, due to the osmosis, what is going to happen? The water molecules from the dilute solution will flow from the concentrated solution. That is due to osmotic pressure. So what is osmotic pressure? It is basically an extra pressure. Now we can correlate osmotic pressure also a colligative property. It depends on the number of particles in the solutions. So it can be correlated. There is an equation that you can see. The pi is equal to CRT. CRT is basically, you can see, that is C is the molarity of the solutions, not molality. In the elevation of the boiling point, we have understand it is molality, depression of the freezing point, it is the molality, but here it is the molarity. CRT is the molarity of the solution. Pi, the osmotic pressure, and CRT. C is the molarity of the solutions, and you can write molarity of the solutions. Molarity of solution, and R is the universal gas constant. R is universal gas constant, and T is the temperature. So these three things will be correlated with the osmotic pressure. Now suppose there is a volume V, volume in V liter of the solution, volume of the solution in V liters, and number of moles present of the solute is N2. So we can write this equation in this way: pi is equal to N2 by V into RT. So we further write pi V into is equal to N2 R into T. This is the equation, and from this equation we can able to calculate the molar mass of these solute particles. That we can understand now. You can write pi V is equal to N2 into R into T. Suppose there is a W2 gram of solute having molar mass. M2 is the molar mass, so we can write N2 is W2 by M2 into R into T. So we can write W2 M2, that is the molar mass of the solute, is equal to W2 R into T by pi into V. This is the equation, and from this equation you can able to calculate the molar mass of the solute. Molar mass of the solute you can able to calculate. Or if we know all those things, that is the amount of the solute we given, one amount of solute will be deposited, dissolved in the solution. If we know the osmotic pressure, and if we know the volume of the solutions and universal gas constant and T, then you can able to calculate the N2. So you can understand that the molar mass can be calculated from the different, that is from your boiling point, elevation of the boiling point, from the depression of the freezing point, and also from the osmotic pressure. But it has some advantages. Advantages is What is the advantages? We can write advantage. Advantage of the osmotic pressure. From the osmotic pressure, we can able to calculate the molar mass. Number one advantage, that it carried out at room temperature. It is carried out at room temperature. Carried out at room temperature. Second thing, this can be utilized to this osmotic pressure to measure the molar mass of polymers. Molar mass of polymers, proteins, and also macromolecules. Different macromolecules we can able to calculate from this. And third point, that the value of this, from this colligative property, value of this value we will get, the value will be higher than other colligative properties. So it can be measured more accurately. So we can write another point, that is the measurement will be accurate. Measurement shall be accurate. So these are three important points that we can get from this osmotic pressure when we are going to calculate it. So that is all for today's lecture. In this lecture we have discussed the two very important things, that is the depression of the freezing point and the osmotic pressure, and from both the colligative properties how we can able to calculate the molar mass, that we have discussed in detail. Thank you very much for watching, and if you like this lecture you can share to his friends. Thank you.